Okay, here's an example of what's known as an Atwood machine. So this thing is a frictionless pulley. It can rotate like this, it can rotate like this, and we have a string suspended over it with two masses hanging off both ends of the string. I'm hoping it's obvious to you that the heavier mass will accelerate downward and the lighter mass will accelerate upward. Okay, so we might even draw an arrow in indicating we know the direction in which this pulley will rotate. So we need to find two things in this example: the acceleration of the masses, so the acceleration of the 5 kilogram mass downward and the acceleration of the 2 kilogram mass upward. Because the string doesn't stretch, and I'm hoping it's obvious that those accelerations will be the same, only in opposite directions. And the tension in the string, and that's slightly more involved. Okay, but the thing about a string, first of all, if you have a string and it looks like this, there's no force in the string. Okay, once the string is taut, meaning being pulled from both ends, it'll be straight, and the way something like this works is the force in one direction will be equal and opposite to the force in the other direction. So you can think of Newton's third law. For every action there's an opposite and equal reaction, or for every force there's an equal and opposite force, and the same holds true for a string. Okay. So, onward. This will give us some room. Here are the forces acting on these objects. The 5 kilogram mass has Earth pulling downward on it. We call that force its weight, so that will be 5 times 9.8, or 49 newtons. The 2 kilogram mass is also being acted upon by gravity. W equals mg yields a force of 19.8 newtons. So what we know from this is that the tension in the string is more than 19.8 newtons, because the 2 kilogram mass is going to accelerate upward. The upward force has to be more than the downward force. We also know that the tension in the string is less than 49 newtons. We know this 5 kilogram mass is going to accelerate downwards, meaning the force upwards has to be less than 49 newtons. So off to the side I might write, I know the tension is going to be less than 49, but I know it's going to be more than 19.8 newtons. Okay, just so that if we get an answer and it's crazy, we know it's wrong and we messed up somewhere. So when considering, when trying to find the acceleration, what we're going to do is we're going to consider the object being accelerated to be something like this. We have the 2 kilogram mass attached on a string, or via a string, to a 5 kilogram mass. And this entire thing is accelerating like this. So the total mass being accelerated is 2 plus 5, 7 kilograms. Okay? And the net force acting on that total mass, the tensions cancel out, the net force acting on that total mass is this minus this. So because it accelerates in this direction, okay, this force is greater, so we know that it will accelerate in this direction. Let me draw it horizontally. Okay, so given this situation, we have 49 newtons pulling this way, and to the left we have 19.8. newtons. So all I've done is I've taken, oops, yeah, that's right. What I've done is I've taken this situation and I've just sort of laid it out flat, assuming this is a frictionless surface, right? Frictionless pulley. 5 kilogram mass attached to a 2 kilogram mass, and in this direction we have 49 newtons, right? And in this direction we have 19.8 newtons. So if you look at it like that, it's obvious that the 7 kilograms of mass will go in this direction, and the net force acting on that 7 kilograms is 49 minus 19.8 newtons. So here we go with F equals ma. F, of course, being the net force acting on the entire system. So we have 49 minus 19.8 newtons, okay, and that is the mass of the system, 7 kilograms times acceleration. Solving gives us an acceleration of 4.2 meters per second squared. Okay. So, I wonder if we're right. If we create another page and look at each of these separately, we can figure that out. So, we have our 2 kilogram mass. In the upward direction, we have the tension. And in the downward direction, this arrow is slightly smaller, 19.8 newtons. We know that the tension should be greater than 19.8 because the 2 kilogram mass accelerates upward. And over here, we have the 5 kilogram mass. We know it's going to accelerate downwards, so the 49 newtons should be more than the tension upward. And we know acceleration is 4.2 meters per second squared in the downward direction, and over here we know acceleration is 4.2 meters per second squared in the upward direction. They have to accelerate at the same rate if they're attached with the string. So we're just going to do a simple F equals ma for both of these to make sure it works. F equals ma. Net force acting on the 2 kilogram mass is, and look at what I'm doing, I'm going to write T minus 19.8 equals m times a. Let me use some parentheses there. 4.2 meters per second squared. So notice how I subtracted tension from 19.8 because it moves in this direction. The tension is the greater force. So it's this minus this. And then over here, with the 5 kilogram mass, I know the 49 newtons is greater than tension, so I might write 49 minus tension is mass times acceleration. And so solving for t, in both of these situations, here we're going to get tension is 28.2 newtons. And over here we're going to get T equals 28 newtons. So this works. The difference in the 0.2 and the 0.0 over here is due to the fact that we used g, or the acceleration due to gravity, is 9.8, and a more accurate value would be 9.81. So if we were to use that, you might do that in your spare time. You should get much closer values. But this works. Okay. Very good.